We're now going to begin a discussion on Chapter 4, which is the second major topic in Calculus 1. It's the notion of antiderivatives. We have already discussed the process for computing the derivative for essentially every function that you're familiar with the exception of the natural log function and the exponential function, and then all the logarithm and exponential functions. We're going to talk about that after we've combed through this work on antiderivatives. So with those two exceptions, you have the process for computing the derivative of essentially every function that you've dealt with so far. This new process, this new topic, is antiderivatives, and really it's essentially you need to be able to do the calculus both forward and backward. And so as we're going to see, this is a procedure for computing a function whose derivative is known. So let's recall a little bit. Let's start with something we know about. Suppose you're given this function. Suppose we're given x to the third minus 5x squared, let's see, plus 4x plus 6. And our task, suppose we want to find the derivative, right? So let's just do this. Let's say this implies the derivative. Now this is just the ordinary power rule. We're applying it to a polynomial. So this should be pretty straightforward. The power rule. Now, what I want us to do is to consider this very slowly. In fact, you've become so adept at this. It's like many things, you do this without a whole lot of deep thought because this has become very much a part of your mental furniture. You understand this so well that sometimes you can do this without really thinking about what's happening. But I want to slow the process down because what we're going to do is reverse this process. So if we take a much closer look at it going forward, we'll have a better feel for how this works going backward. So the power rule says this. The power rule says for the derivative here, you multiply this exponent times this coefficient. In this case, the coefficient is 1. Take this exponent, multiply by the coefficient, and then subtract 1 from the exponent. Now, let's just take a piece of this. Before we finish this out, let's do a smaller issue. Let's suppose we have g of x is, let's say, 4x to the second. Now, when we compute the derivative, think about what actually happens. You multiply, first thing you do, the first thing is coefficient multiplied by this exponent. That's the first computation that happens. And then the second computation is you subtract 1 from the variable, from the exponent. This is 2 minus 1. Now, we don't do all this detail work. What we actually do is 4 times 2 is 8. 2 minus 1 is 1. Now, the procedure is the first thing you do, where did this 8 come from? The 8 came from the first thing you do, which is multiply this value, this coefficient, times this exponent. And that's where the 8 comes from. The second thing you do is you have a 2 that changes to a 1. How did that occur? What happens is you subtract 1 from the exponent. Now, imagine that you run this video backward. You started with 8x to the first, and you end with 4x to the second. But it's not all in one time. When we run the video backward, what was the first thing that occurs when you run backwards becomes the last thing that occurs. And what was the last thing that happened when you run forward becomes the first thing that happens when you run backward. So, going, if you will, in this direction, going from G to G prime, the first thing that happens is you multiply the coefficient. The second thing that happens is you subtract from the exponent. But remember, running the video forward, subtracting exponent. If this exponent had been 5, this would have been 4. If this had been 9, this would have been 8. If this had been 12, this would have been 11. So running the video forward, you start with 9, it becomes 8. You're subtracting. But when you run the video backward, 8 becomes 9, 4 becomes 5, 11 becomes 12. What's happening when you run the video backward? When you run the video backward, you don't subtract 1, you add 1. So when we go from this expression backward to the top, the first thing that happens is you adjust the exponent. And the adjusting is you add 1. So when you start with 8x to the first, and you want to find the function whose derivative gives you 8x to the first thing that happens is you add 1 to the exponent. So 1 becomes 2. Now, what happens to the coefficient? 8 becomes 4. 10 would have become 5. If this had been 20, this would have become 10. If this had been 2, this would have been 1. What's happening? You divide this coefficient. But what do you divide it by? Do you divide it by this exponent? No. You divide it by the exponent you just created. So you add 1. So if we start with g prime and we want to find our way back to the original g function, suppose this weren't present. We want to run the power rule in reverse. The last thing that happens when you do the power rule, if we had this function, the last thing we would have done is subtract 1 from the exponent. Well, when they run the video backwards, subtract becomes add, and this becomes the first thing you do. So the first thing is you add 1 to the exponent. And then this 8 needs to get divided, but do you divide it by this one or this 2? This value is, we know it needs to be 4, because it is this value divided by, the phrase I use is the exponent you just created. You add 1 to the exponent, and then the coefficient is divided by the exponent you just created. Now, there's a little more to it than this, but for now, let's use this. And so let's see what we have, the power rule. This reverse process, the power, if there's nothing magic about 2 and 1 and 8 and 4, if we had started with g prime, suppose we were given the derivative as x to the n. Let's actually alter that just a hair. What if we had been given a x to the n? What was the function, the original function whose derivative would have given us ax to the n? Well, what's the first thing you undo when you reverse this process? Yes, the 1 becomes the 2. If this had been a 5, this would have been a 6. If this would have been a 12, this would have been a 13. You add 1 to the exponent is the first thing that happens. So the first thing that happens is this x is now raised to the n plus 1 because we are reversing the process. And then how did we get this? How did we take this 8 and change it into this 4? Yes, you divide this coefficient by the exponent, but which exponent? Do you divide by the original exponent here, or do you divide by the exponent in the original function g? Yes, this is the exponent you divide by. You do not divide by the n. See, in this problem, n is being played by 1. You don't divide by n. We have to divide by this number, which is the n plus 1. And so it is the value a divide by n plus 1. So we're just reversing this process. Again, there's a little more to it than this, but for now, this is going to be sufficient. And so we can now take this principle. If I have h of x is 7x to the 4th, reverse this process. So in this case, a is 7, n is 4. This is the derivative we've been given. So this implies what is the original function h from which this would have come? What's the rule? Add 1 to the exponent. So this becomes x to the, you tell me, x to the 4 plus 1 is 5. And then you divide by the new exponent you just created. This becomes 7/5. Now, in this scenario, this coefficient simplified. In some scenarios, the coefficient doesn't, but that's sufficient. Now, again, all of these are going to have one little detail that I'm glossing over for now. We'll pick it up here in just a moment. But one thing you can always do is this. When we started with 8x to the first, and we worked backwards to find what we thought was the original function, we should be able to check our answer. How can you check to make sure we did this correctly? Do you see that if you take this function and compute the derivative, you better get back where you started from. And sure enough, the derivative of that is 8x to the first, which is what we wanted it to be. We can check to make sure this is correct by computing h prime. And sure enough, if you multiply 5 times 7/5, the 5's cancel, getting 7. And then x to the 5 minus 1 is 4. So yes, this is the correct procedure for reversing this derivative process. What we have found in the terminology is an antiderivative. Antiderivative. 4x to the second is an antiderivative of 8x to the first. And so this is the power rule antiderivative happening here. So let's get back to our original problem here. We're given f of x, the derivative. Well, the derivative of f of x is straightforward. The derivative is, I think it's straightforward, 3x to the second minus 10x. I'm going to put all the little details in here. 10x to the first plus, remember what this is? This is actually 4x to the first. So this is 4 times 1, 4x to the, technically this is x to the 0. And then what's the derivative of a constant? The derivative of this constant is 0. All right, so I'm going to steal some space here on my board. Let's simplify that. That's 3x to the second minus 10x plus 4. All right? But we remember, this really is 4x to the 0. Now, what we did was, when we took the derivative of all these linear functions, linear expressions, linear terms, what we said is, essentially, you're applying, really what you're doing is you're applying this power rule and getting 1 times 4 and then x to the 0, which simplifies to 4. But we sort of abbreviated this notion by saying this, as the lawnmower goes on outside. You feel like you're at the college now. When I have 4x to the first, the short version is this. For a linear expression, for a linear term, the derivative is you lay the variable aside. Don't think of it as drop the variable off. Think of it as lay the variable aside. Because now what we need to do when we go back, suppose this weren't given, and we needed to backtrack our way up the trail. Suppose we need the original function f now, and all we were given is this expression. We need to do here what we just did over here. We need to reverse. This is the derivative. We need to find the antiderivative. All right? So what's the process? Add 1 to the exponent, divide by the exponent you just created. So 3x to the add 1 to the exponent, divide by the exponent you just created, minus 10x to the add 1 to the exponent, divide by the exponent you just created, plus. Now remember, this actually is 4x to the 0, right? So one way to think of it is add 1 to the exponent, divide by the exponent you just created. A little shorter way to think of it is this. When we started with 4 times x, the derivative is lay the exponent to the side. Well, now you're going to be glad you laid the exponent to the side. Remember where you put it, because now you need to pick it back up again. So the derivative of a linear term, x to the first, the derivative of a linear term, lay the variable aside. It's a constant. The antiderivative of a constant term is a linear term. So you need to pick the variable back up. Now, the question is this. If all we were given is this, we're not sure how to handle this. I'm going to kick that can down the road for now. Let's simplify this. This is x to the third minus 5x to the second minus 4x. This is the function we originally started with. One exception. It's the 6. Right? So we actually have a plus 0 here. The derivative of a constant is 0, so the antiderivative of a 0 is a constant. So we could put the 6 back on here. Now, a reasonable objection to this is, there's a couple objections to this. One is, if all you were given is this expression, if this is all you were given, and you wanted to work backwards to see which function it came from, you would not have known that it was 6. That's one problem. Another problem is this. What if this original given number had been 7? This derivative still would have been 0, and then we need to back our way back up the trail to find out we would have needed to have chosen 7 here. What if this original number had been 70? Then we would have needed to have a 70 here. The issue is, if all you're given is the derivative, you don't know the constant that might have been attached to there. And so we're going to talk about that in the next video. For one thing, I'm getting overruled by the lawnmowers. And so we'll talk about that in the next session.